Have you ever held an ice pack against your skin and felt it grow colder even as the ice melts? That's because melting is an endothermic process. The solid absorbs heat from whatever surrounds it to break its molecular bonds and turn into liquid. But could some unusual solids absorb so much heat during melting that they actually make their environment noticeably cooler, even without blowing on them or adding more ice? What's really happening when a solid melts? Every time a solid turns into a liquid, it needs energy, called latent heat of fusion, to overcome the forces holding its molecules in place. Question: where does that energy come from? Answer: from the surroundings. If you melt a block of ice on your skin, the ice sucks heat out of your flesh, making you feel cold. That's the everyday endothermic melting mystery at work. Are all melts equally cooling? Not quite. Different materials require different amounts of energy. Ice needs about 334 joules per gram to melt. Bismuth needs around 11 joules per gram. So melting 1 gram of ice chills your hand far more than melting 1 gram of bismuth. If you want maximum cooling, you pick a high latent heat substance. Ice is hard to beat at common temperature. Could we find solids that cool faster or colder than ice? Yes, and chemists and engineers have explored salts and alloys for phase change cooling packs. For example, mixtures of ammonium nitrate or urea with water can absorb more heat per gram than pure ice when they dissolve or melt, making them popular in instant cold packs. Question: why don't we use ammonium nitrate more often since it's even more endothermic? Because it's messy, corrosive, and in pure form can be hazardous. Ice, by contrast, is safe, clean, and readily available. What about exotic materials? Researchers have looked into metal organic frameworks and certain salt hydrates that melt at room temperature with huge latent heats, potentially cooling electronics or buildings without electricity. Imagine a tiny pad of material that, when it melts, keeps your laptop several degrees cooler just by borrowing heat from the components. Can melting ever cool below the solid's melting point? Here's a twist. If you cool a system quickly after melting, the temperature can dip slightly below the normal melting point before the solid reforms. This is called supercooling. It happens with water in a freezer. It stays liquid below 0 dDc until you disturb it, when it instantly crystallizes. But during the melting itself, the temperature of the substance remains at its melting point until the last crystal dissolves. In every case, the mystery isn't that melting cools. You can feel that with an ice cube, but how cleverly we can harness materials with high latent heats and safe handling to create passive cooling systems. From emergency cold packs to future self-cooling electronics, endothermic melting remains a surprisingly powerful and perfectly accessible trick for dropping temperature simply by letting solids turn into liquid. Endothermic melting refers to the process in which melting absorbs heat to break molecular bonds and transition from solid to liquid. This energy is called the latent heat of fusion and is required without raising temperature during the phase change. However, the environment around the melting material may or may not feel cooler depending on how the heat is drawn in. Typically, heat is absorbed from an external source like air or contact material, so the melting solid doesn't cool its surroundings, it draws in heat from them. But certain cases suggest a paradox: melting that draws in more energy than expected, causing net cooling locally. Ice melts at 0 dEc by absorbing latent heat from its environment, creating a cooling effect. Used in drink coolers and cold packs, it's like a sponge soaking up heat instead of water, leaving the environment drier in thermal energy. Materials like water ice, paraffin, and salt hydrates absorb significant heat during melting, a principle used in cooling packs and thermal regulation systems. As these materials melt, they hold temperature constant while absorbing energy, preventing surrounding air or surfaces from warming. This is exploited in phase change materials, PCMs, used in smart textiles, building materials, and electronics. The cooling effect is not because they generate cold, but because they withhold temperature rise by absorbing heat. Yet in all these cases, they don't actively reduce surrounding temperature below ambient without external heat flow. Cold gel packs melt while absorbing heat from an injury, offering relief without dropping below freezing. It's like pressing pause on heat. The material halts rise in temperature while it soaks in energy. In rare scenarios, the surroundings can feel cooler during melting if the system draws heat faster than the environment can replenish it. This effect can appear in materials that have exceptionally high latent heats or melt at unexpectedly low temperatures, triggering rapid heat absorption. If the ambient temperature is just barely above the melting point, the material's demand for heat can chill nearby areas as it pulls in energy. However, this does not violate thermodynamic laws. It's an imbalance of thermal flux. The local temperature drop is a relative cooling, not absolute cold generation. When ammonium nitrate dissolves and melts in water, it absorbs enough heat to significantly chill its container. Used in instant cold packs, it's like one person taking all the blankets. Everyone else suddenly feels colder. Some substances dissolve with strong endothermic reactions that resemble melting, but involve bond breaking and salvation, not phase change. Salts like ammonium chloride or potassium nitrate absorb large amounts of heat when dissolving in water, creating rapid, localized cooling. These are sometimes mistakenly interpreted as melting cooling events, but the chemistry is different. In dissolution, new interactions form between solute and solvent, requiring energy to disrupt original bond. While both processes absorb heat, melting alone rarely causes such extreme cooling. An instant cold pack activates when a salt dissolves in water, cooling the pack dramatically within seconds. It's like mistaking evaporation for melting. Both absorb heat, but through different escape routes. Some advanced materials under investigation in thermochemical energy storage can absorb vast quantities of heat upon melting or phase transitions. These include metallic glasses, certain salt hydrates, and nanostructured PCMs with modified thermal behavior. In confined geometries or near critical conditions, their melting may induce heat absorption sufficient to lower adjacent temperatures. These effects are studied for spacecraft thermal shields, data center cooling, and wearable tech. They don't break the second law, but they push its engineering limits. Sodium sulfate decahydrate absorbs large heat loads when melting, used in thermal batteries and solar heat storage. It's like discovering a material that acts like a thermal sponge, pulling heat away faster than expected. Some substances supercool stain liquid below their freezing point until a seed triggers rapid crystallization, which may release heat. The reverse of this, melting under metastable conditions, can demand sudden and intense heat absorption. When this occurs in a poorly conducting medium, the surroundings may cool perceptibly. These transitions are sensitive to impurities, geometry, and vibration. Supercooling reversibility plays a key role in dynamic thermal environments. Supercooled water at maximum DHC begins to melt only after mechanical agitation, rapidly absorbing heat and chilling nearby fluid. It's like a sleeper waking up suddenly and needing food fast, pulling resources instantly and unbalancing the system. At nanoscales, melting behavior deviates from classical models, melting points drop, surface effects dominate, and phase transitions become fuzzier. Quantum dots, for example, can absorb energy without sharply defined melting points, entering mixed or metastable states. These behaviors can lead to anomalous thermal fluxes during transitions, including conditions where nanosystems extract heat from their surroundings in unpredictable ways. Advanced calorimetry and cryogenic studies reveal subtle energy absorption signatures that may resemble cooling. Quantum coherence may also play a role in how energy is redistributed. Melting of nanostructured ice films on graphene surfaces shows energy transfer patterns distinct from bulk melting. It's like ice melting pixel by pixel on a screen. Each point behaves independently, but still influences the whole. Endothermic melting does not violate the second law of thermodynamics. It redistributes energy, but always within a closed energy budget. Any perceived cooling while melting is a result of energy being drawn from the surroundings, not created from nothing. Claimed violations usually ignore boundary conditions, misidentify dissolution as melting, or overlook ambient heat contribution. The second law remains intact. Entropy still increases when solids melt, and heat flows from hot to cold overall. It's the dynamics, not the direction, that seem mysterious. In all documented cases, entropy calculations show net energy conservation and disorder increase despite localized cooling. It's like borrowing money. You may seem richer for a moment, but the balance sheet always settles. Endothermic melting can create cooling effects under specific conditions, particularly with high latent heat materials, supercooling, or nanoscale systems. These effects don't defy physical laws but reveal how phase transitions can create surprising energy gradients. Advanced materials science is harnessing these transitions for applications from cold storage to thermal logic gates. The mystery lies not in impossibility but in complexity, the balance of latent heat, molecular structure, and environmental flux. The cold that comes from melting is not magic, it's beautifully misunderstood physics. Engineers design PCM-based building materials that absorb heat during hot hours by melting silently in the walls. Cooling without fans or electricity, it's like a ghost absorbing warmth from a room, not breaking the rules of physics, just following them in an unexpected way.